Hello everyone. I'm going to go over the example we did with the node voltage analysis, and I'm going to use the mesh current analysis to solve the same circuit and obtain this, hopefully the same node voltages as we did with node voltage analysis. If the methods are correct, then both methods should yield consistent results. So now, when we're doing mesh current analysis, we need to identify the mesh currents. So that's our first step. So then we can pick how we choose our mesh currents, and a very easy way to do it is always to do the inside, the smallest meshes that we can identify. So just like what has been drawn here with IA to IE. Now, this is a complex circuit, and one thing that we can notice is the way that these mesh currents have been drawn is that we have a supernode here because we have a current source shared between two meshes. And one way I could have gotten around that actually is redefining this IE mesh current and maybe making it like so all the way around here. I could have said that that was IE, and then this 2 amp current source would not be shared between two meshes. It would only be associated with IC. However, I chose not to do that because I want to show you how to do a super mesh as well in this example. Okay, so then what's our next step? We develop the mesh equations associated with each mesh. Okay, and then we notice, of course, we have a super mesh that is shared between IE and IC. Now, the green circle or green shape denotes the super mesh. Now, how do we draw this shape? I mean, it doesn't have to be quite like that. Maybe we could have drawn it on the inside, okay? Maybe we could have done it this way. So what's the important thing about this super mesh drawing? What it should do is encompass the meshes that we're referring to, because we're going to write the super mesh equation in terms of the individual mesh currents enclosed by the super mesh, okay? And then when we write the super mesh equation, we ignore the current source that's enclosed within it, the one that's shared between the two mesh currents. Okay, so let's go ahead and start solving for or developing the mesh equations. Now, the first thing that we can notice is that for the IA mesh current, we see that there is a current source, a constant current source, which is the 0.25 amp current source associated with that mesh current, okay? So this current is going in this direction, and it's only shared by IA. Its value is 0.25 amps, and since it's the only current associated with the mesh current and it's in the same direction of the mesh current, it's equal to IA. So this is great. We have one of our mesh currents identified with almost no effort. Okay, so then let's keep going. Let's do the equation for mesh B, which is associated with the IB mesh current. Okay, so then what does that equation look like? Well, now when we're making our mesh equation, we're considering all of the terms within it to be voltages. So this is a voltage, a voltage, and a voltage. Okay. So then, how do we get that? So then, what we consider is that, let's say I'll use maybe my dark blue. When we're looking at the IB mesh current, it's a direction of travel. It's going up this way. Okay. So then the voltage of the 4 ohm resistor is going to be identified with the 4 ohm resistor being multiplied by the IB mesh current, and we see that the IA mesh current is in the opposite direction of IB. So we have IB flowing up this way and IA flowing up this way in opposition. So that's an IA. So then that's why we have a minus sign here for the IA mesh current. Okay, so that is where we get those terms from. Okay, when we keep going, we're going to see the current controlled dependent voltage source up here. So now, what's the voltage of this device or of this component? Well, the value is actually given right here. It's 4Ix. So that is actually the voltage. Even though it says Ix, the constant scalar of 4 has implied units that convert that Ix current into a voltage. So that's why when we write 4Ix, it's actually a voltage. Now, notice when we're traveling around in the clockwise direction, we see the current, the negative sign of the voltage source first. So that's why we have this negative sign here in the equation. Okay? And then we keep going around and we see the 1 ohm resistor. So we have the 1 ohm resistor multiplied by the mesh current itself, and we see that the IC mesh current is in the opposite direction of IB. So then we have a negative IC. Okay? And then everything has to equal 0 because of KVL. Okay? So this is equal to 0 because of KVL. Okay, so that's how we construct the equation for the mesh current, and let's do the next one for mesh D. So mesh D is over here. Okay, and then the equation is going to look like this. So you can study that equation. It's used the exact same methodology as for mesh B, and it should make sense to you. So we're going up through the 4 ohm resistor. IB is going this way. IC is in opposition, so hence we have ID minus IC for the 4 ohm resistor. For the 4 ohm resistor, we come across to the left. IB is the only mesh current associated with the 4 ohm resistor, so it's just ID. And then when we come around, when we keep going around, the first sign that we see in the voltage source is a plus. So that's what we see here, and the value of that voltage source is 10 volts. So we have 10 volts. Of course, all equal to 0 because of KVL. So now we do the super mesh equation. So what's that going to look like? Well, the super mesh equation, it's one equation, but it's composed of 2 parts. One part is the mesh E part, and the other part is the mesh C part, okay? And it's combined. So then we write the equation, and it looks like this. So what's happening here? So let's say we start here, we come around this way, and we see the positive sign. So we see a positive 4ix, okay? So that's what we have here. So that's the voltage of the current controlled voltage source. Then we come around this way, go through the 1 ohm resistor, and then the only mesh current associated with it is IE. So now we are done with the IE side of the super mesh. So this is the mesh E side of super mesh. Okay. So then we come around to the other side, keep going down, and we go through the 4 ohm resistor, and that's what we see here. And so now we have the IC mesh current in that direction, so we have a positive IC, and the ID mesh current is in opposition, so we have minus ID. And then we come around, go through the 1 ohm resistor, and then we have the IC mesh current and in opposition with IB, so it's minus IB equal to 0. And so then this side is the mesh C side of super mesh. So now there's one other thing that we can notice with this circuit, and that is this. We notice that IC is the branch current, and that's controlling the current controlled voltage source, okay? And that branch current has a relation between the associated mesh currents. And it's in the same direction as IC and in the opposite direction of ID. So we can notice that this term is actually IC. So we can just capture that information for us and just write it here because we're going to need that later. We're eventually going to write a system of equations that is going to be composed of the variables for IA, IB, IC, ID, and IE. So that's the point of doing the mesh current analysis, is to develop numerical values for the mesh currents. And then from there, interpret what we're going to do to further analyze the circuit if necessary. Okay? So then, now, the next step in this analysis is to consider that, hey, we did this trick so we didn't have to find a voltage expression for a current source. That's why we use the mesh current analysis. But we can't forget that that device is still in the circuit, because the circuit would behave differently if that was that device or that circuit element had a different value. Okay, so now what we have to do now for the super mesh analysis is to develop the dependence equation. Okay, so we got to do the dependence equation that relates the current source, okay, which is 2 amps, and how it relates to IE and IC. Okay, and this is the relationship that it has down here, where we have 2 amps is equal to IE minus IC. Okay, the 2 amp source is in the same direction as IE, right? IE is going this way, through the 2 amp source, and then IC is going this way. Okay, IC. Okay, so that's what this equation indicates. Okay, so now what do? Well, we have a system of equations now, and now we have to do some mathematics to analyze it. So what we're going to do is simplify the equations and substitute in our relationship for Ix. Okay, so we're going to go step by step. So we already have the relation for IA. We knew that it was 0.25 amps, and we're going to do mesh B. Okay, so now I'm just dropping the units and just simplifying the equation. So I've got the terms, and over here I have substitute in for IX. Okay, so this is IX, so that's this term here, and then I can further simplify that in green just below, and I'm putting it in somewhat of a standard form with starting with IA on the left hand side and moving all the way down to ID on the right hand side. Okay, and then we can do some simplification for the mesh D equation, drop the units, multiply things out, and then collect the terms, and then we have the simplified expression in green. We can go further for the super mesh equation. So what I've done here is I've substituted in IX, or the equation for IX here, okay, and simplified the equation, dropped the units, and then that simplifies to the equation in green, and then simplify the dependence equation, drop the units, put it in kind of like a standard form, although I could have switched the positions of IE and IC. And then, so then we're going to have a system of equations, okay, and I'm going to write IA in green as well, and I'm going to get rid of IX because we don't need that equation anymore because we substituted it in. So then we have now the system of equations in green. Those are the simplified equations, and then we can go ahead and use some math to solve for the individual mesh currents. So we know what IA is, and then we're going to solve for IB, IC, ID, and IE. Okay, so there's going to be a little bit of algebra there, and you can use your linear algebra tricks to simplify this. But there's going to be a little bit of math here that I'm going to skip over. But in green are the basic equations that you're going to use. You have 5 equations, right? 5 equations and 5 unknowns that you're going to solve for, okay? So you're going to work on those equations. So then, when you solve, you're going to get these values, okay? So you're going to get IA, well, we knew IA anyway, that was an easy one, 0.25 amps. IB is 0 amps, that's interesting. IC is minus 2 amps. ID is minus 2.25 amps, and IE is 0 amps, so that's interesting. Okay, so then, now we've solved for the mesh currents, okay, and now the second part of this question was to calculate the node voltages by using the mesh currents. So how are we going to do that? Okay, well, we're going to need to set a reference node, okay, so for the node voltages to make any sense. And what I'm going to do is I'm going to follow the example for the node voltage analysis example, and I'm going to use the same node voltage, which is, the same reference node, which is down here. So that's 0 volts, okay? So we know that that means that this node is 0 volts. And then I will label the node voltages with the same names as I did with the node voltage analysis. So that's VC, this is VB, this is VA, and this is VD. Okay? So I'm going to use these mesh currents to solve for the node voltages, and hopefully we get the same results. So then, first thing I notice is that VD is equal to 10 volts. Now I don't need to use my mesh currents to solve for this because it's obvious immediately that VD is equal to 10 volts. Okay, on this side it's 0 volts, And because this is a 10 volt source, this side must be 10 volts. So VD must be 10 volts, okay? We don't need to use mesh current analysis for that. Okay, so then let's do the other node voltages. So what we're going to want to do is calculate the branch currents so that we could find the node voltages. Because if we knew, let's say, the current flowing through here, right, if we knew that I, then by knowing the resistor value, we can calculate what VC is. Okay, so that will be fairly straightforward. So we're going to find the branch currents, and we see that the circuit has a nice structure that if we find the branch currents here and here, then we'll find all of the node voltages. Okay, so let's continue. So I'm going to label all of the branch currents. So I'm calling this one I1, this one I2, and this one I3. So let's go ahead and solve for I1 using the mesh current. So what's the relationship for that? Okay, I1 is in the same direction as IA, okay? And it's in the opposite direction of IB. So what's I1? I1 is equal to IA minus IB. So we can put in the values, and then we get the I1 branch current as 0.25 amps. Okay, so going down here is 0.25 amps. That's what that means. So we found the current that's actually flowing through that resistor in terms of the mesh currents. Okay. And then, if we know that, if we know I1, then we can easily calculate VC by using Ohm's law. Okay? We know the current through the resistor, so we know what's the voltage across that resistor. So then, this is our equation here. VC is equal to the current times the resistance, okay? And this only works because we know that this point here is 0 volts, okay? Because that's the reference node, okay? That whole bottom part is the reference node. So that's 0 volts, so when we're calculating VC, we're actually calculating the voltage across here like so, VC, okay? So anyway, this is the equation, we put in the values, and then we get VC voltage of 1 volt. So that VC is equal to 1 volt. Okay? And then we can continue our analysis. And then we have the I2 mesh current. Okay? And when we look at that, right, it's right here. It's in the same direction as IB, so it's equal to IB. It's in the opposite direction of IC, so it's minus IC. We put in the values and we get 2 amps. So that is 2 amps flowing through this resistor, 2 amps. Okay? I2 is equal to 2 amps. We can do the same analysis to find the voltage. So the VB node voltage is the current times the resistance, and that, of course, that only works because this end here is at 0 volts. Okay, so we put in the value for current, 2 amps times 1 ohm. We get a voltage of 2 volts. So that is equal to 2 volts. VB is equal to 2 volts. Okay, we keep going. And we calculate the I3 mesh current. Branch current. Oops. So we're doing I3. So that's I3. And it is in the same direction as IC. So we have it's equal to IC. It's in the opposite direction of ID. So it's minus ID. Put in the values and get a current of 0.25 amps. Okay. Now, so that's the current through here, right? That's 0.25 amps, and that's also the same as IX. So this is also equal to IX. So for some reason we wanted to find the actual value for the voltage. The voltage is 1 volt, right? 4 times 0.25 amps. But we're not solving for that at the moment. We're solving for the VA voltage, and what is our expression for that? Again, using Ohm's law, we have VA is equal to the current, I3, times the resistance, plug in the values, and we have 1 volt. So then we say that VA is equal to 1 volt. So in summary, these are all of the node voltages here. We've solved for the node voltages, and we notice that these node voltages are exactly the same node voltages as when we did our node voltage analysis. Okay? So this example shows how to use mesh current analysis, how to implement it, and then how to interpret that mesh current analysis to determine node voltages. Okay? So this is a complex example. It shows using the super mesh, and it also shows using a dependent source. If you understand this example and the same circuit using node voltage analysis, then you're doing well and you have a good understanding of circuit analysis up to this point in the course.